Hello everyone, welcome to this lesson. So in this lesson, we're going to be starting a new series. It's called curve fitting. We're going to be starting with the first technique, which is linear regression. Then we're going to be progressing to polynomial regression. Then we're going to go through a little bit of linearization for more complicated functions like power laws and logarithms and all these types of functions. Then we're going to end this series with interpolation by introducing one of the most commonly used interpolating techniques called cubic spline. Now, in this lesson, we're going to start with the simplest of all regression analysis, and this is linear regression. So usually in science and mathematics, there's a lot of observation, there's a lot of data collecting. So basically, let's assume you had collected 12 data points, 12 pairs, and you have them here, x from 1 to 20, and you got the corresponding y's. And when you graphed them, you found that you got a linear trend. So based on that linear trend that you observed, you want to fit a linear model to those data points that using this model can basically predict any value outside of this range, because within this range you got between 1 and 20, and now you want a model that can predict everything after 20 and everything before 1. So in this case, we're going to be employing a concept called the square of the sum of the square of the residuals, and by reducing the sum of the square of the residuals, we're going to be finding the best fit for these data points. So what is a residual? Where a residual is actually very, very simply the distance between the measured y, which is any one of these points here, and also the prediction of the model that you're trying to create. So when we're trying to get the best fit for these data points, we're trying to reduce the distance between the measured y and also the model. So it doesn't come as a surprise that we're trying to reduce the distance between the points and the model. So since here we're dealing with a linear model, the y here, the yi model, is going to be defined as a naught plus a1 xi, where a naught is the intercept and a1 is the slope. And this is basically two pieces of information that you require to define any linear line. So what we're trying to do is we're trying to find the a naught and the a1 that would best fit these series of points. So those are the two pieces of information that we're after when we're performing linear regression. Now, if you've noticed here, we're dealing with reducing of an error, which means essentially linear regression is an optimization problem. We're reducing residual error. So it wouldn't come as a surprise that here we're going to be dealing with getting critical points and getting where the derivative is equal to 0. So a residual in this case is, so the yi, which are any of those points, those are constants. So we're dealing with two variables here, a naught and a1, and we're trying to find the value a naught and a1 that corresponds to those two derivatives being equal to 0. So since we're dealing here with two independent variables, we're going to be dealing with a partial derivative. So we're going to be getting first the partial in terms of a naught, and then we're going to be getting a partial in terms of a1. So, and then we're going to be placing them into 0, and this is how we're going to be creating the model for linear regression. So let's actually create the partial in terms of a naught. So if you saw this is actually a chain rule because we have an outside function, which is basically the squared here, and we have an inside function, which is basically what we have in here. So the outside function is basically we use the power rule, so it's just going to be 2 multiplied by this sum. And the inside, since we're going to be taking a derivative in terms of a naught, all of this is just going to reduce to -1. So this is where the negative came from. Then we're going to place this equal to 0. We're going to do the same thing for the derivative in terms of a1, and you're going to find that the derivative outside is still the same, 2 multiplied by this sum, but the only difference is when we take the derivative in terms of a1 inside, the xi is the only thing that remains. So we multiply here by xi, and we replace this equal to 0. Now, if we take this and we distribute the sigma inside, we come up with this expression here. So we have the sigma of yi minus sigma a naught minus sigma a1 xi equal to 0. We do the same thing here. We distribute the sigma. We have this here, the sigma yi xi minus sigma a naught xi minus sigma a1 xi squared equal to 0. Now we're going to apply a few sigma rules, and this is it. Basically, when you are summing all the a naught, basically a naught is a constant, so this is going to be n a naught, where n is just the number of data points. In this case, we have 20. And another rule of the sigma is that if you have a constant within the sigma, it can actually go outside. So we're going to take the a naught outside. And also the same thing going to happen here. We're going to take the a naught and a1 outside. And we're just going to rearrange all of these in this fashion here. So we're going to use these and we're going to perform some algebraic manipulation, and we're going to get an equation for a1. And we're going to find that a1, when we use these two equations, is going to be defined as n. Again, those are the number of data points multiplied by the sum xi, yi. And the way you get the sum is basically you multiply each one of these points and then you add them all up. And then is minus the sum of all the x points multiplied by the sum of all the y points divided by the number of data points multiplied by the sum of xi squared. So basically you're going to take the square of each one of these points, then adding all of them up, minus, then we're going to take the square of the sum that we have created in the numerator. So once I have a1, I can easily get a naught by getting the average of y and x. So the way you get a y bar, which is the average, is basically you take all the sum of all the y, which is sigma yi, and you just divide it by n. And also x bar is the sum of all the x's divided by n. So now I have a1 and a naught that would create the best fit line that would fit these data points. And the thing that I want you to notice here is that a1 and a naught are defined entirely in terms of the points here. So that's all you need. All you need is the x points and the y points, and then you create from these based on those four different sums, including and also in addition to the average y and x, you have the a1 and a naught that would create the best fit line, which is very, very neat that there is really no techniques, no advanced or complex manipulations that you're doing. All you're really doing is making sure that you have your data points, sum them in these four different ways, and also getting the average of y and x, and now you have the a1 and a naught that will create the linear line that would best fit your data points. So it's pretty neat, it's pretty simple, and it's very, very effective, as we will see in the next lesson. The last thing that I want to talk about before I end this lesson is something called R-squared. And R-squared is something that we will use to measure the effectiveness of the model. For example, let's assume my R-squared is 0.80. And what that means is that the model that I have created describes 80% of the behavior of the points that I was trying to model. So it's pretty good. So what if I have, say, an R-squared of 0.99. What that means is that my model describes 99% of the behavior of all my data points, which means this is a very, very great model and have captured the essence of the data points and captured the essence of what you're trying to create a model for. This is going to be basically defined in terms of a quantity that I will define in the next lesson called ST, and also in terms of the residual error, which we have defined here, the sum of the square of the residuals for each one of the data points. So we're going to be defining basically what that is in the next data point, as we are going to be actually fitting a linear line to this set of 20 data points. So to kind of recap briefly what we've learned in this lesson, we have introduced linear regression, which is basically you would use to create a linear model. And basically we have employed a concept called the sum of the square of the residuals. And we said that the residual is the distance between the measure points, which is the ones that you have here, and the model we're trying to predict. And we said that since here we're dealing with a linear model, is going to be defined as a0 plus a1xi. And the purpose is we're trying to find the value a0 and a1 that would best fit these data points. We also mentioned that this is an optimization problem, which is why we got the derivative at a in respect to a0 and the derivative in respect to a1, and we placed these equal to 0. We distributed the sum inside, got those two data points, and then we applied the sigma properties to get these two versions, and then these two equations created the a1, and also factoring in the average of y and the average of x, we can use this expression here to get a0. So very, very simple. And also we have defined that a1 and a0 are defined entirely in terms of the data points. So if there's one thing that you would take out of this entire lesson is linear regression. If you know these two equations, that's all you really need to know about linear regression. And of course, this is also the last thing that we have introduced, R-squared, which is basically to see the effectiveness of your model. How much is your model describing or capturing the essence of your data points? Is it capturing 80% of it, 90% of it, 99% of it, and so on? So that's it for this lesson. And next lesson, we're going to be developing the Python code for linear regression. Thank you very much, and I'll see you in the next lecture.